Have anything really else to add except that Don is going to tell us a little bit about the Cincinnati Observatory, some of its history, and he'll be here with us after the conversation for people that want to go upstairs and see the telescope up there. It looks like a couple of people got sneak peeks on that. Yeah, good way. So, anyway, take it away, Don.
Thank you. Well, how many have been here to the observatory before? Okay, we have several. Well, welcome to the birthplace of American astronomy. I'm going to give you a real brief overview of our observatory. This observatory was founded by Ormsby McKnight Mitchell. And his story is he went to West Point, graduated. He came back to Cincinnati after fulfilling his duty there. And he taught at a local college here, the Cincinnati College. He gave speeches about astronomy. He could draw hundreds of people. After drawing these crowds, some people approached him and said, you know, let's start the Cincinnati Astronomical Society and build an observatory. And that's what they did. They took up subscriptions, $25 per share, raised $7,000. He went to Europe, found the telescope, bought it, and this was one in the other building, the original telescope from 1845. They built the original observatory on Mount Ida, downtown Cincinnati. John Quincy Adams, former president, came to dedicate the observatory, and they renamed Mount Ida to Mount Adams. And if you go up there today, where the monastery is, the big red brick building, that's where the observatory was. Mitchell was killed during the war. And the observatory didn't do much. In 1868, they got a new man, Cleveland Abbey. He came here and said, it's in disrepair. You need to do something, find a new location, because everybody was burning coal downtown. You couldn't see anything. But he did notice one thing. He noticed the weather from the west, what we got here a few days later, was the same weather. So he made a deal with Western Union, and he had many locations, west and north and south of us, send us their actual weather, and he started publishing weather forecasts here in Cincinnati, the first ones in the U.S. 1870, when they finally created the United States Weather Service, first leader was Cleveland Abbey from the observatory. The Cincinnati Astronomical Society didn't have money to build a new observatory. They gave all the assets to the city of Cincinnati. They combined that and some other assets and created the University of Cincinnati. We moved out here in 1872. John Kilgore, if you're from this area, there's Kilgore School, very wealthy man. The railroads was Kilgore. The telephone, Cincinnati Bell, was Kilgore. He said, I'll give you 4 acres and $10,000. He put it right here. And that's where it came. And that's how Mount Lookout got its name. So they did all sorts of work here on stars. This room is actually part of the observatory. The center part here, this concrete, there used to be a telescope in here. And that telescope only looked in the north-south axis. All that was open. And from that, they could tell a couple things. One, whenever certain stars would cross this meridian, they knew exactly what time it was. We were the timekeepers for Cincinnati. We used to have a time ball here, a big one. There was one down 4th and Walnut. That was one of the things they did here. They also did charts to say what was the position of stars out there. From declination and right ascension, like latitude and longitude, they charted all these stars. And that's what they did here. Later, skipping a lot, but in the early 40s, they took out the telescope here, and we got a computer. 1947. And there wasn't room for the telescope and the computer. Because remember, the computers had these card punch machines, and these sorters, and all these different things. And they used that in here for several years. We were the minor planet center of the world. Paul Fergus, who was the observatory director at that time frame, his kind of claim to fame was he was outstanding at figuring orbits of things. He was calculating orbits of some of the moons of Saturn. And then when they started the space program, it was Paul Fergus they called upon to say, how do you calculate the orbits? How much speed do we need to get to where we want to go? And that's what he did. That's one thing he did with the computer. And if you look back at Project Mercury and some of the early projects, you'll see Paul Fergus's name mentioned many times about that. Later, 1978, Paul Fergus retired. The observatory basically closed down at that time. It sat here empty until the 90s. And they wanted to do something with these buildings. The neighbors didn't like it. So after a little negotiation, these became National Historic Sites. And the Cincinnati Observatory Center took over. We operate the facility now. The land is still all owned by the University of Cincinnati, but we're more into education here. Now, we're operating museums and education. We have outreach programs where people come here to see the stars or planets. We have outreach programs for children, and that's what we're doing through today. I know that was very brief. Do you have any questions I can answer? Yes?
I've never heard the term time ball.
Yeah.
I imagine some kind of globe that is registering and marking the time.
You ever, on New Year's Eve, watch them drop the time ball on New York Square,
Yeah.
Times Square?
Yeah.
Same thing. You see that bolt in the wall right there? There used to be a big hole on the outside, it was 6 foot. Every day at 1/4 till noon, ball went halfway. 5 till noon, went all the way. At noon, it dropped. We kept the time here. We have clocks like this. Downstairs, we have 2 other big clocks that are in a vault, underground vault. So the temperature doesn't affect their accuracy, and that's what we did here. And there was another clock or another time ball downtown, 4th and Walnut.
And how did it move?
Basically, a rope and pulleys. They pulled it up to the top. There was someone here who did it manually.
Oh, just how would you know? Thank you.
But a long time ago. Everything was manual. Yes.
So how do they know what was a 1/4 till noon and so on?
How they know what time it was? With a telescope in here, they could see whenever certain stars, clock stars would cross. That tells them the exact time. They'd set their clocks, and they use these clocks then to raise the ball and to drop it.
Okay.
There was a thing called Cincinnati Standard Time. If you look at a newspaper back in the 1870s, 80s, they would show railroad schedules in both Central Standard Time, and they say add 22 minutes for Cincinnati Standard Time. Why 22 minutes? There's 24 time zones in the world. We're in the middle of one, and they want to know the exact time where that period is out there. And that's the reason it's 22 minutes, because astronomers work with the exact time where they do their observation.
So when we're late, we could say we're on CST.
The Cincinnati thing.
Good to know. Okay.
Well, welcome. Later, if you'd like, I will take you up and show you the telescope. If you have any questions at all, feel free to ask me, and I'll try to answer it if I can.
Thank you.
So, I think that means we're starting. So, per tradition, we're allowed to take our masks off as speakers, right? So I'm going to do this because my ears are killing me. Yes, so today at this marvelous location, we want to talk about space. We want to talk about the concept of space in various circumstances, and not just the exploration of space, but also, I don't know if you've read through the announcement. Now that I'm going to refresh your memory, so we want to talk about space as the in-between. And we want to talk about space as the void between objects and people, but also that space is so much more than just the emptiness between things. It is actually something that we shape, that we make place in, that we call home, that means something to us. We have some kind of fascination with it, being that the void out there, the big space that we want to explore, or the space that we create to live in, or the space that is, trying to understand what is between these things, like the very smallest spaces that we can detect. We have a fascination with this, and this is what we want to talk about today. So I have invited a couple of amazing people. I have actually invited a lot more than these people, so if you've read the announcement, you may notice that these are probably not the people that you've been expecting. So we had 2 speakers cancel because of personal emergencies. But we have a wonderful short notice guest, Melissa Jacquard, who is an assistant professor, right? Assistant professor in philosophy at UC. And she is also the associate director for the Center for Public Engagement with Science. And her research focuses on epistemological issues in the philosophy of science, and that around the use of models and computer simulations in astrophysics. How fitting. Yes, and I have a couple of very interesting questions to ask later, but I am getting to that. And maybe I'm going to go around, I had a beautiful concept for all of this. This is not happening, so I'm going with whatever comes to my mind. But I thought with your introduction, you could give me a brief idea on what the kind of space relationship it is that brought you here, or how you make a connection to space in your work.
Yeah, sure. So I actually work on outer space. I specifically work on dark matter. So most of the universe, all the universe that we can see, everything that we can see, planets, you, me, all the atoms, only make up 5% of everything that's in the universe. The other 95% we cannot see with our eyes, and so we call it dark matter. So my research focuses on how do scientists actually see basically invisible things that they can't see with their eyes. And so I look at how they conceptualize things that they can't see and how they actually go about trying to see things that they can't see. And so I look at how scientists use gravitational interactions, so sort of bodies acting on other bodies to try and see things because they're interacting with other things, and how scientists as a whole think that that's either super bizarre or weird that we can't see things, or perfectly reasonable, perfectly normal.
Wonderful. That's going to be so exciting. Thank you. So I'm going to stay in the realm of physics, and I want to introduce Adam Orizano, who is who is an associate professor. Assistant. I'm sorry. We'll get there. Assistant professor at the UC Physics Department. And he is a particle physicist, so he studies the smallest pieces that we know, in particular neutrinos. And so he can potentially tell us something about the very smallest spaces. So that sense in or are somehow detecting between the smallest pieces of matter that we are aware of. So welcome, and could you give us a brief introduction to what your relationship to space and space research is?
Sure. Like you said, I study particle physics, but specifically neutrino physics. So neutrinos are not something that I think most people have a familiarity with, but they're actually, I don't know if one of, maybe the most populous particle in the universe. So there are millions of neutrinos going through your body right now, right? So the sun, all nuclear reactions produce neutrinos. So the sun is producing neutrinos. They pretty much just ignore matter. So they're going through the Earth right now from the other side of the Earth and going through your body as well. And they are unusual in the sense that there's 3 different types of them. And as they travel, they tend to turn from one to the other. And so there's actually sort of maybe 2 different sort of dimensions of space that sort of come into play in neutrino physics. One is the very small, so neutrinos are very, very small, and we study them by watching them hit atoms in a detector. or so basically they hit the nucleus of the atom. And the details of what happens depends on sort of what those neutrinos see. And this sort of will get into sort of this idea of this in the smallest space, right? What exactly you're seeing in the smallest spaces changes as you look on a smaller and smaller level. So depending on exactly how much energy that neutrino has, it sees kind of a different reality inside that nucleus in different different ways. That's what controls what you wind up seeing in our detector. The other thing is that the thing that we actually really care about is how the neutrinos are changing from one type to the other. And it turns out that happens as they travel. So we actually have to shoot our neutrinos over a long distance to make this happen. So we're starting sort of for really small distances, but we actually make our neutrinos at Fermilab in Chicago and send them through the Earth to a site that's far away and measure them there. So there's an experiment that's being built now that will be located in an abandoned gold mine in South Dakota. And so the neutrinos will travel 1,300 kilometers, basically, through the Earth before emerging in that gold mine where we will have a detector sitting. So because this stuff happens based on both like their energy and the distance they travel, we tend to have to sort of go over these really large distances and sort of like we measure stuff right when we create them and then we measure them again really far away and essentially see what's changing over that distance. So we wind up seeing stuff in sort of both relatively large distances as well as like in the actual detection of them really, really small distances.
That is fascinating. The ratio of the smallest thing that we cannot see with the eye, and that we take these enormous distances to measure. Wonderful. No, I'm geeking out on these. But I also want to introduce the rest of the speakers. Sorry. No. So this is Paula Silva. Welcome. Paula is a physiotherapist and associate professor in psychology. And her research focuses on action strategies. So you might wonder why she's here. Now, Paula is interested in how people move, especially when they face certain pathologies or movement disabilities. And for that, I invited Paula because she can tell us a little bit potentially about how people use space, right? So how people act in space and make use of the space around them and how what they perceive as available space actually allows them to perform these activities.
It's much more mundane. I started my career as a physical therapist, and I found complicated when we were treating individuals with movement-related disabilities that they had these goals, right? They wanted to walk independently on the street. They wanted to move around up the stairs of their houses without so much help. And the way we were treating them, we were focusing a lot on the kind of mechanics of the body. We're treating the body like this, like a machine. And we looked at, oh, there's strength missing, so we strengthened them. Oh, there's flexibility missing. Enhance their flexibility. And by changing those components successfully, they still wouldn't get to function. Like, what does it mean to move our bodies effectively around the spaces in the world? That's what got me into psychology. I got into psychology because I was interested in how we behave, and that has to do with motor behavior for me. That's my focus. How do we actually move around? And I'm saying it's mundane because movement is so much part of us that if you do not have movement difficulties, you don't think about it, right? You wake up in the morning, you go about your business, and you never think, where should I put my leg and how should I move my leg to get out of the house? And you don't think about these things. But if you, for example, suffer a stroke, or if you even have chronic pain, you start thinking about how you move your body, and that becomes more of a complicated thing to do. So I started to try and understand this in the context of perceiving the world, how we organize movement, how we move with respect to the changing environments that we have around, how do we adapt to environments, and that necessarily implicates perception. So if you're treating If you're treating people, and bodies as machines, you're completely ignoring the fact that we need to adapt our movements to spaces, right? And he was talking about neutrinos changing what they are as they move, and I think that's what we do as people. We use the same parts. Right now, we're using it to become a sitting device, but sometimes we're making our bodies move in ways that we're a cloning device. So the same parts have to be organized in different ways in our goals or functions, and that's basically what I'd like to understand. How do we relate to spaces? How do we perceive space in ways that allows us to behave effectively in those spaces? And how do we create spaces that actually can support the function of people with disability, for instance, so that we make spaces that are more inclusive? So that's the kinds of things that I'm interested in. That's how I relate to space myself.
Perfect. See, I'm the IRiS lead for transdisciplinary research for a reason. And, I can talk this because I'm also invited Rob. And Rob Giuliani is, and I am not pronouncing this remotely.
You got it.
Perfect.
You got it.
Thank you. Is an associate professor of history at the UC Blue Ash campus, and his work focuses on the intersections of social and environmental issues. We got involved a lot talking about urban spaces and the history of urban spaces. And I invited Rob because he had he opened my eyes to the concept of placemaking within available space. So welcome, Rob.
So I was thinking about this, and thank you so much, right? Because it got me thinking of the way to approach this question. And one of the things I wanted to talk about was, the difference between space and place and that overlap and that interaction, right? So, think about when you move to a new house or new apartment, right? And I'm an academic, and for those of you who are grad students who think about going to academia, it's a great field, but you end up moving around a lot. And I've moved, my wife and I calculated it up, and we're at like easily above, 20 different apartments, various races. But the first time you walk into that place, right, walk into that apartment, wrong choice of term, right? It feels unfamiliar, right? It is a space, right? And you've chosen it for particular reasons, right? And you might have all your stuff moved in, right? It doesn't quite feel like home yet, right? It is a space, but it's not a place yet. It doesn't have that meaning to you, right? And so that's the sort of an entry point for it to think about that. It has a variety of different meanings to you. Well, I'm an urban environmental historian, which means I look at change over time. I look at the role of the natural world at different scales. But I'm also interested in the various forms of social inequality and how they play out over time in those places, right? And so let's go back and think about that home. So my current research is focusing a lot on the role historically in the United States of the sort of political, economic, social, cultural construction of the single family home, right? Who gets to own that single family home in a particular neighborhood? What is the social meaning, particularly the racial, class, and gender meaning of that home, right? A Marxist scholar would look at the construction of space there, right, and how the spatial construction confers a sort of a monetary value, right, an exchange value, but also a use value. But then I'm also interested in the environmental impact of that home, right, both in terms of the actual space it occupies. Is it on a small lot? Is it on a big lot? Does it have a lot of trees? All those different things. Is it a solar house, right? Does it have lots of glass block? Does it use a lot of energy? But also, and this kind of connects with what Adam was saying, thinking about it on the environmental impact at scale, right? And these different scales. So usually environmental historians, when they talk about this single family home and its environmental impact, they focus only on the community and the neighborhood. But what I'm interested in is, all right, what is the impact of that home if the home is 45 minutes away from your job, and the only way to get to your job is by a car, and you have to drive to that car, you have to drive to that job every day 45 minutes. So the environmental impact of that is not just the lot it occupies, but also all the petrochemicals and carbons you're using every day, right? And that's impacting all these different other places, right? And after the Super Bowl, my Twitter feed blew up, not as a Bengals fan, even though I'm a Bengals fan, but and that is not the role I have it on Twitter. I'm an academic Twitter, which is very stressful. Mine was sort of commentary on all the electric vehicle ads, right? Which was great on the one level, but you have a lot of very critical environmental studies scholars, and they go, it's still a car, right? If you buy an electric car, yes, maybe you're not having environmental impacts on a well drilling site in Venezuela, but the environmental impact is a lithium mine in Uruguay, right? So thinking about that scale.
Fascinating, fantastic. So now I've probably blown your mind in the different concepts of space. So let's get this down to the bottom a bit. And, obviously, as always, feel free to ask questions at any point and interrupt me. But I wanted to start talking a little bit about, with all your different approaches, how do we sense this kind of space, right? So Adam has told us a little bit about it. This has pointed us to the fact that it's invisible. And maybe you want to start by talking a little bit about how do you, in your field, like in this context of your work, how do we detect the space? How do we sense the space?
Yeah,
That
sure.
is so invisible, because I look around and I see a lot of things. I don't really see space, right? The space is the in between.
Yeah, and I think this goes for a lot of astronomy. So for anybody who may be familiar with astronomy, you might know that there are many ways that you can observe things in outer space. I like to talk about this in terms of my friend Maya. So Maya is an observational astronomer. She can look out, she can look up at the night sky. We could go out right now or with the telescope later and look at it. And what you can see with sort of the naked eye is sort of the first level of things that you can see. And so Maya, the observational astronomer, she can go out with her eyes and see things. But one of the really neat things about scientific advancements in astronomy is we've developed all these other telescopes that basically allow us to, in some sense, put on other eyes to an extent and look into outer space. And suddenly, through these different lenses, we can see so much more. And so this is a whole spectrum of things in terms of X-rays, like the kinds of X-rays we see in our body, gas, all these kinds of different kinds of eyes that we can put on and observe. And so for a lot of the history of astronomy, we've been able to find these other sets of eyes that we can adopt and put on. But we've finally gotten to a point where we've run out of those eyes in terms of things that we can actually see. And we finally found a type of matter that exists in the universe that we actually can't see with anything like our eyes. And at least from what we know right now, the only way we can see it is because it interacts with other things that we can see. And so a big question is that enough of a reason to think something is there? Because you can see it interacting with something else. Just because we can't see it with our own eyes, should we privilege our own capacities to see things? And so I basically am trying to think through, like, how does a scientist in particular who wants facts and wants to be able to, like, find the thing and put their finger on the thing, go about justifying that kind of thing? And so some scientists are perfectly fine. Like, we've had all of these other sort of exposures to these kinds of things. Why should we think as, like, humans we're privileged in any other capacity? And that there's this new thing, and yeah, that's just how we see it. But there's something very, like human about being like, I wanna really actually see it. I don't want you to just tell me it's there and believe it's there. I want something more concrete. And so one of the only other ways to get super concrete about that kind of thing is be like, well, maybe if I put it in a computer, maybe the computer will help me be able to see it. And so computers have really, in many ways, in sort of like many of these fields, have really helped us be able to see these sort of invisible things, at least in the way that we can interpret it and interact with it.
So what is the computer doing that's helping us see? What does that mean?
Yeah, so it's able to like tell you, it's able to give colored dots, essentially. It's like, okay, so you think there's this tiny little bit in the of matter in the center that we can see in sort of like a bit of space, like a galaxy, for example. Like we can see a bit of space. A galaxy is a very small thing. And so we can see that, and so we'll put that into the computer, and then those will be red. They're often red. And then we'll say, okay, all this stuff we can't see is going to be all these blue dots. And so we assume that they're blue dots, just the same way they're red dots. And we put that into the computer, and then we just like smash stuff together sometimes. But putting it in that sort of way gives it some sort of thing that we're familiar with, that we can identify and interact with in a way that we know how to interact with. And so that's one of the ways that they try and make that invisible stuff visible, is by putting it in the computer and at least allowing us to interact with it in that way. And then we just sort of assume that the same things hold in the real world as well.
Do you have similar experiences with small spaces?
Yeah, I mean, you can't see really any of the things that are on the particle physics realm, really. And there's a lot of so we have sort of the scale that we live in, right? Sort of like the human size scale. And we have a lot of intuition about how that works, that we just build through experience, right? Our brains are sort of primed to sort of grasp that. But sort of one of the big surprises of modern physics, right? The beginning of the 1900s was realizing that there are different scales where things are very, very different from the human size scale that we live in, and that they're true in ways that like we can see the consequences of, even we can't see them themselves. So that's true on the really ultra big scales for astronomy, but it's also, as you go smaller, sort of you have quantum mechanics start to take hold, right? Well, quantum mechanics is true always, right? I mean, this is the thing. So like relativity is true always, but in our everyday life, we don't move very fast. And so it doesn't matter most of the time. Quantum mechanics is true always, but like we're relatively big and those effects don't generally matter to us, so we use them for stuff all the time. But as you make things smaller and smaller, things become more and more quantum, right? So they just act differently than you would intuitively expect, because our intuitions are built from something totally different from that. And so one of these things is that theoretical physicists will often use this thing where they talk about natural units, right? So they sort of say there's a couple of constants that sort of dictate like the main behavior of our world. So like relativity is based on the speed of light, right? That's sort of like, that's the benchmark speed that all other speeds are compared to, because nothing can go faster than that. And then there's another constant called Planck's constant, which is sort of like gives you the scale of when quantum stuff starts to matter. And so oftentimes theoretical physicists take all of those constants and say, we're just going to make them all one. And when you do that, length and time are the same unit, and energy is 1 over length, right? So the idea is that as you go to smaller and smaller scales, that's equivalent to like looking at higher and higher energies, right? So in some sense, when you narrowing your focus to smaller and smaller spaces, you're looking at things that are happening at much higher energies, right? So what you kind of see, what's sort of like, often people talk about this as saying that empty space looks very empty, but as you peer in with a smaller and smaller microscope, you start to sort of expose this sort of roiling landscape. One way to think about it is energy is conserved, right, in sort of all the like reasonable time scales in the universe. But it turns out that the ledgers of the universe are only sort of kept on like a certain time scale, right? So in some sense, if you're looking at really small times, which is the same thing as looking at really small lengths, you can fudge the books as long as you fix it before the time's over, right? Sort of. So it's sort of like this like virtual particles, where like particles will pop in and out of existence. As you go to smaller and smaller scales, you have stuff popping in and out of existence. And we call them virtual because they can't like travel in a life of their own, right? They sort of like pop in and out. They just are like transient things that pop in and out. And it's one of these things where like we look at them so we can't actually see that. So like, is this real or is this just sort of math, right? Because like a lot of times we do math and we say, is this stuff really there? But one of the things I find interesting when I talk to my students in class and I start talking about some of these weirder things, they always ask that, like, but I mean, is this really real? Like you can do the math and the math sort of says that. But you can do stuff and show that you can do things and you can observe something that wouldn't have happened if this stuff wasn't true. So the classic one for these virtual particles is something called the Casimir effect. Right? So the idea is if you take two metal plates, right? The idea is that quantum mechanical particles they're particles, they're also waves. And in some sense, in the space between the plates, virtual particles that have wavelengths that can fit inside between those plates can pop in and out of existence. And as you make the plates smaller, you're basically limiting the wavelengths of something that can pop in and out of existence. Now, all of these are virtual. They don't really have a life of their own. But as you make the plates closer and closer together, eventually the pressure of all these virtual particles on the outside of the plates gets to be bigger than the pressure of the ones on the inside. And the plates push together. And so it's like there winds up being a force that's actually generated by these things that don't ever actually have an independent life of their own. Right? So it's like you can do that and show that there is something happening on these smallest scales that sort of when you do something that probes those smallest scales, you get a real like macroscopic visible response that you wouldn't have been able to see otherwise. So we wind up seeing this all the time where there's these weird effects that don't necessarily act the way you expect as you go to probing smaller and smaller distances. And despite the weirdness of all that, this is what happens when we build particle accelerators all the time. And we take particles, we accelerate them really fast and we hit them into each other, and energy is like one of our links. So those really high energy particles are like probing really small distances, and you wind up seeing like particles come out that are much, much heavier than the ones that you sent in. Right? And one way of thinking about that is that you're sort of like pumping energy into that sort of sea of virtual particles, and you give some of them enough energy that they get to be real. Right? Like they stop being virtual and they start to have a life of their own because you sort of gave them enough energy that they're not sort of cheating energy conservation anymore by doing that. So you basically can sort of like pump energy into the vacuum and make stuff come out that wasn't there before, or at least like wasn't manifest before. And so we do that sort of every day, and like people at the like Large Hadron Collider do this at like really high energies. But it even happens on like this happens naturally, right? There are particles coming and hitting our planet that are higher energy than anything we can make in a lab. Like we can make particles that are really high energy, but there are cosmic rays, which are just basically like particles that have accelerated, distant galaxies that have been traveling through space and hit our atmosphere. And we see that. We have sort of detectors where, like the instrument, there's a detector called IceCube, for instance, in the South Pole, where they basically drilled holes in the ice and they dropped a bunch of detectors down it and instrumented a cubic kilometer anyway, of ice.
The skills are one anyway.
And when you do that, you can see things like you will see a bunch of particles that all come sort of in parallel, all at the same time. And we realized when you do that what happened was like this super ultra high energy particle hit the atmosphere and just had this explosion of particles that it sort of pulled into being as it went and sort of spread out. And, when we set up detectors all over the place, and you can see that, those sorts of air showers, they call them, can wind up spreading out over miles and miles and miles and miles. So there's some of these that have energies that are, unbelievably high that people can see. So despite the fact that you can't see any of these things yourself, right, the effects can be huge, right? So like if you can sort of build the right, I think what you're saying, like the right eyes, and you can see their effect even if you can't see the thing themselves.
And I think it ties in some ways to your work. I mean, part of what happens in a lot of physics and astronomy is this expectation that things are going to interact in your space the way you expect them to. And a lot of times what happens in some of the greatest discoveries in sort of physics and astronomy is when things aren't interacting in your space the way you expect them to.
Yes. And I think there's, one of the things that you mentioned that's interesting, that we bring a level of curiosity when we're studying the small, the tiny scales and big scales that sometimes we don't bring when we're studying that scale of behavior, because we have some intuitions about it, but it doesn't mean that those intuitions are correct if you probe them. So you start finding much more mystery in the movements. Just as one example, when we think about the number of parts that have to coordinate in order for you to even be sitting there or for you to walk, we're talking, 100 muscles, even to move just your arm, okay? So how do you, it's about, I shouldn't say 100, 100 is your whole body. We have about 10 muscles to move just the arm. And you may think, 10 is not a lot. Okay, now think about if you're trying to drive your cars, and instead of just controlling the direction and the speed, which is two things, you had to control each wheel independently. You had to control four parameters at each point in time. How hard that would be. So what our body does, imagine just to control the movements of your arm, that you have to transform in different ways. If you have to pick up this cup or this cup, it's a different type of force that you have to put in there, different type of grasp. All of those things are different, and we do it so fluently. And people try to describe it in terms of the forces that you need to do. Newtonian mechanics is the kinds of laws that will be important and relevant, and we can't violate them. There is a particular amount of force I have to put in here for this to be lifted. But the combinations of muscles that I can use, the combinations of movements that I can use are multivariate, right? So it's not just one or two. How do our brains pick? How do our brains control all of these pieces at each point in time? And I'll tell you more. And that's when space comes in. And when we think about movement of the body, and traditional disciplines would go in kinesiology, you would look, or anatomy, you would look at where the muscles insert, inserts in this bone, So in this position, like completely, imagine you're laying down without any forces acting on your body like this. In this position, when if you're an anatomist, you go there and shrink the muscle, and you see how, the bone that's heavier won't move, the bone that's lighter will move. So you can say, your biceps is this, right? The calf muscle, if you're standing like this, and you want to just, bend your leg like in the gym, this muscle would help you do and bend your leg. If you're sitting like this, and you want to extend your knee, the same muscle will be used. Do you know why? Because your feet are planted on the floor, it's heavier to move the whole floor, or the floor will stay stationary. So the same muscle can extend your leg. So depending on your relationship to space, different muscles will come into play, right? And I think the beauty of this is that when you start taking context into account, and you start taking the multiplicity of possibilities that we can use your body to move effectively, you start thinking that for people with disability, they may move differently, but we shouldn't be trying to put them in a mold. Imagine if you had a stroke, or if you're a kid with cerebral palsy. The traditional way of thinking about treatment still today is to take the neurotypical person and get the average way that person moves, and we try to get the person with disability and make them move that way. Because of course they're not functioning well, because they're not moving that particular way, right? And we forget to explore the multitude of possibilities that movement can occur effectively, right? And that is if you read qualitative studies of people with disability, that's something they say, that the experience of disability can be made worse by physical therapists that insist that they need to move this way, right? When they're already figured out, especially little kids with disability, that they are used, they have been more open from the beginning to explore different ways of moving. There's a lot less, they're less jaded when they're kids, because of course as you grow older, now you try to conceal that because of how other people react to you and your body, right? But little kids, they figure out ways to do sports and things, And then physical, no, I shouldn't move this way, I should move that way. And if you think about their movements, when you look at their movements and you think, oh, their brain is messed up, the movements take advantage of the bigger resources they have. You know, it's very beautiful actually. So if you think of kids with disability, like hemiplegia, for example, CPs, kids with cerebral palsy, they walk like, they have a bouncy gait. They, instead of walking like pendular, like most people do, like you swing your legs back like this, the leg that is unaffected by the disability, they generate force there in the calf muscle, but instead of pushing the center of mass forward, they push it up, such that it falls on the other leg that can produce force, but it has very stiff muscles that conserve energy really well. So the movement is not stupid that they're doing, it's actually taking advantage of the properties of their body, right? So how can you help them? How can you help extract out of them the kinds of movements that can make them move and behave effectively in this environment? How do you use the environment to support the extraction of those movements, including our social environment, right? Because I keep thinking that that's one barrier that eventually I'll encounter in my work, that, you know, that people will say, but I do want to move normal. Because we put these things, I mean, we're socialized in a way that, you know, walking, like bouncing around, people might not perceive that as something that's okay, right? So how do we celebrate those?
Also the
Those
spaces,
spaces moving,
the
right?
spaces and the places that we live in are created for the neurotypical person, right?
Yes, yes.
By shaping the space and making the space more accessible, we can potentially create more opportunity.
And you know, a lot of people, you know, the movements of people with disability, they push a lot for, my disability has not so much to do with my body, it has more to do with how the space is received. And I think this is very true. And at the same time, it is true that we can do things with the body to make them, to help them move more effectively. If we just freaking give up the idea that we have to make them move like the norm, right? And help the society be less encumbered by it somehow, you know, so that people can wish different things and move normal. Yes.
I have a question for you. Thank you so much. I'm very much interested in the question of mental space or psychic space now, because all of you are touching upon actually materiality as one of the defining factors how we can define space. But mental space as well as psychic space, I would argue, operate in different parameters. Let's phrase it like this. I'm very interested after what you've been saying, Paula, how to take this into account, especially with the example of disabilities, where the mental space as well as the psychic space might be different ones and might not match what normal, quote unquote, normal people perceive as spaces. And I would, you know, none of us shares the same mental or psychic space. Can you go a bit more into it? Because I think it's doing very well to get this what you've been
I mean,
saying.
the concept of mental space is tricky for me. I try to study how we think about space and how we think about the world. And I do, if you're saying mental space in the sense that we all might have different experiences in space, I think that's very real, and there's a lot of research to suggest that. For example, if you have a person holding a backpack and ask them to judge the slant of multiple, they will judge it as steeper than if you're not wearing a backpack.
And what it also means that like you organize your internal space. Oh, no, another concept for space, internal space. Okay, forget the street concepts right now. But actually, in a way, how we internally organize space for ourselves, either our ideas, how we perceive the world, whatever. And then I'm saying it touches upon all of you because one of the concepts that was there was perception. Space is perceived. Even you talking about the neutrinos, you said they are perceiving, and I was like, whoa. No, I really have to question, how do you know they perceive?
Right.
Sorry, no, I'm not questioning, but it was really interesting for me because it's like, how do you know they are perceiving? How are they subject and agent and have an agency? This is really interesting for me.
Yeah, I mean, so it's sort of, maybe what I would say is that I think this is sort of like this idea of scales, right? That the same physical thing can be very different depending on what scales you're on. So I think the thing that I was kind of thinking about when I was saying that was, you know, we think of materials are made out of atoms, right? Atoms are mostly empty space, right? So it's you have a bunch of electrons on the outside, and then a nucleus that's really tiny on the inside. And the electrons sort of stake out the boundaries between them, right? So that the atoms are sort of like stuck apart from each other based on like how far the electrons are from the inside. But if you go in and you zoom in and look at the nucleus looks like it's a thing, right? It looks like an object, but it's very, very dense compared to everything else. And when you have a particle comes through, and a particle has relatively low energy, it sort of interacts with the whole thing, right? So in some sense, that's what I mean by perceiving. It sort of perceives it as an object, right? Because it comes in with relatively low energy, and the sort of like scale of distances that it's probing is relatively large. So it sort of probes the whole nucleus as like one unit. But if you make things go a little bit faster with a little bit more energy, you wouldn't see it as an object anymore. You would see it as a bunch of protons and neutrons. Right? You'd see it as nuclei, right? As nucleons, right? And so you see it as a bunch of protons and neutrons that are all sort of swirling around each other.
Who is
right?
the you, though?
Well, now we're doing the imaginary you, where if you could be that small and moving that fast. Right? So I guess that like, physically, the thing that we can see is that if you take a probe particle, it's like a neutrino, and you send it at relatively low energy, then the neutrino can scatter off of the nucleus as like a whole thing. So there's a thing called coherent scattering, where the neutrino interacts with the nucleus as a whole, and that the thing that we notice is that the nucleus vibrates basically when it was hit, and that's all you see. Is the nucleus?
Yes.
The nucleus just sort of recoils, right? And so people have made detectors to look for this because it was something that was hypothesized to happen, and relatively recently, people were able to detect it where you essentially sort of take something that's ultra cold, right, where sort of the atoms in it aren't moving very fast on their own, and you sort of wait to see sort of reactions. So there's like they'll make like detectors that are made out of things like silicon, right, solid like semiconductor type stuff, and have them like down at like very, very cold, almost absolute zero temperature. And when you're that sort of low of a temperature, when one nucleus is sort of pushed on, it causes like a sort of a sound ripple that's sort of like a particle, right? So we call them phonons. They're like it's really like the collective movement of like you start one thing moving and everything moves in a collective way that travels like it's a real particle, though it's really like the movement of a bunch of stuff. And they can measure that in those sorts of devices, right? Where you can sort of see that there's this like quantized amount of sound that just happened in this device, and that we know something hit it, right? And so those sorts of like coherent sort of scattering that scattered off the whole nucleus is something that we can tell that neutrino was interacting with the whole thing all at once. It wasn't interacting with part of it. And so it's sort of like, it's sort of hard to see, like that's sort of like the best you can do in terms of like, because we can't actually do that small. You can't actually see it, right?
I find it interesting in this whole concept, like all of the concepts that we've heard so far, it's about the interaction, right? It's about something is happening, something is reacting, and we can perceive this reaction, and then we act upon what we perceive about this action. And then it's a circular effect, but I actually had several questions.
Oh, I wanted to kind of draw a theme out about handicap, actually, because there's a thread running through this, which is interesting. One is how handicapped we are by our intuition for the scale we operate on, right? This is handicapping our capability to see really important parts of the universe so to the extent that we actually need to translate things to meet our handicap in order to even interact with them, like your example. But what's interesting is that also our experience handicaps our ability to meet people in their own real situation and imagine how they might become more effective versions of themselves as well. It also handicaps some of our ability to think about the scale of impact that we have on the world around us. We're not, our psyches are not really evolved to think at the global scale, to think about the lithium mine in Uruguay as something that should guide our decision about that shiny Tesla that we want to buy now, right? So it's interesting. I've been thinking a lot about intellectual humility of late and how handicapped we are by what actually empowers us to move through space. I think if you become too humble, you get paralyzed because you can't decide decisively to move through space based on what you know in your own immediate experience to be true. Anyway, it's this interesting tension that I thought I'd throw in between what our experience enables us to do and what it really handicaps us to experience and understand.
I also love that we tie the concepts of space and time and that they're just indistinguishable and everybody who studies physics knows that. Sometimes we forget this, especially at time scales that we cannot really perceive, like the very small, very short-term effects or larger scale effects that we do not perceive on a daily basis, right? We don't move through on a daily basis.
So I have you mentioned psyche, but I also want to throw in emotional feelings. So I know you mentioned, I'm just going to use your example. So you mentioned moving to different apartments and stuff, and you're like, this doesn't feel like a home, it's a space. But I'm curious to know, as the space changes, or your perception of the space changes, is that also simultaneously with your feelings, or is it okay, everything in the space has to change, and then my feelings will be this feels like something, or is it as it slowly transitions, do you emotionally, and I guess you can throw in the mental aspect in there as well, kind of step along with it side by side, or is one further along than the other? If I'm making sense.
That makes sense. I mean, I would come at it more from sort of the social storing perspective, right? So another person has a different perspective, right? So for me, it would be a both and, right? Because you're identifying certain things with that experience as you're in that space, right? And you have particular experiences with your family, with your friends. You make connection with your neighbors and with your community, right? Or you don't make connections with your neighbors and with your community. And so that those emotions and that feeling ground you in that place, right? And create that. What I'm also really interested in, and this is where sort of an earlier theme we were at, which is sort of expected and unexpected, I'm also interested in how, both historically and contemporarily, that expected and unexpected experience within space and place, and this gets back to what you were saying, right? Gives, it sort of shapes our power relationships. Right, and sort of one other aspect of what I've been looking at is the racialization of space within the metropolis, right? And if you have an expectation, particularly if you're sort of majority white and you have a particular expectation of this community, right, is going to be something that's quote unquote safe for me, right? That's what you're doing when you're purchasing that home, right? And you have all the sort of expectations of political economy in there. But then this is where it gets into sort of mental experience and emotions. All of a sudden, and this is something that sort of human geographers look at a little bit more, which is if you have these expectations about a particular place, but then there can be particular experiences, right, that to you are upsetting that experience of that space, right? And the racial experiences, as we know, can be extraordinarily powerful. Right, that sort of when we think about racism within the metropolis, right? We have these sort of TV sitcom special episodes, right? That we had when I was a kid, right? It's a very special episode. We're going to talk about racism on Family Ties, right? We burned a cross in your neighborhood. That's not how that shit happens, right? It is about, I happened to see a black family at the grocery store, right? Or I happen to have this particular experience, and we have this, right? I see this historically when I look at sources, but also I perceive it when sort of, family members or friends will make conversations that will be, and I don't even call them sort of dog whistle racism anymore, just race in a different language, right? But it's these particular things but what is it doing? It's upsetting what someone's expectations are, right? And they have these expectations of what this space should be, and it's kind of connecting, right, to some of these other things we're talking about, the expectations of what movement should be and how someone should move through space versus what they expect to move through space. And what I'm interested in is that more connecting to what you were talking about, how our social systems are constructed, right, and how everything is oftentimes working against disabled people, right, to be able to, well, hey, I've figured it out in my head and in my body. If you could just figure out and how to work with me as a physical therapist or work with me in a school, right, or something like that, right, then we can move through the world a lot better, and I think that's the other thing here, so.
Can I just complete this? There is this interesting data it's an experiment that they did with kids with disability, and they were reporting on their experience, their feelings of how good they felt collaborating with different people that were helping them in a task that they couldn't do fully by themselves. So it was something about moving an object, and they needed help because they couldn't quite reach out. And they worked with a complete stranger. They worked with a physical therapist, and they worked with a caregiver doing the same activity, right? And one of the things that they reported is like negative feelings, like it didn't go well with the stranger at all. It didn't go, the best it went, it was with the caregiver. With the physical therapist, something in the middle. And the interesting thing is that they did some quantitative work on watching where the eye of the collaborator was, what the person was looking at, the helper. Where were they looking at? The stranger was looking all the time at the person's hand, as though like kind of objectifying the body, right? So just looking at how the hand is moving and really trying to anticipate things, and kind of the physical therapist was like in a mix of looking at the person and at the movement, and like in this attempt to normalize, like if the movement is kind of getting out of hand, like push it like to the norm. And the parent, I think it wasn't necessarily the parent, but the caregiver was looking all the time at the kid and kind of taking their lead. So the kid was all the time leading the movement, and the parent was complementing without worrying about pushing them out of any trajectory that was fundamentally working. And that changed the actual emotions that the kid was reporting about that experience. So there's something about being able to truly coordinate with that person, like really coordinate. And that takes, and I think it's not just a matter of necessarily prejudice, it's also a matter of training. We resonate, it's easier, there's lots of data showing it's easier for a person that plays basketball to predict the outcome of actions of basketball players than other people that watch as much people playing basketball than them. So, but don't have the experience, like sports journalists, they're not as good. The coaches are not as good. So if you don't have the same kind of body, not necessarily you'd be great from the get-go to receive this. You have to have this openness and curiosity to work with them. And that is something that tends not to happen a lot, because people are not occupying as many spaces as they could be if spaces were more accessible and all of those things. There's so many people with disability, we don't see them as much, right? So it's a matter of how do you, like in treating kids with disability, it's always known that parents are really important and stimulating them and all of that. But we don't have anything to train the experience of them. So it's always like, don't let the foot do this because it's bad if the foot. But sometimes you have a kid I treated one time with quadriplegia, that she used this movement that was like, no, don't let it. It's horrible for them. If they do this, the foot will be stuck like this. But that is the way she would express yes. That was her way of communicating, yes, I want this. How do you prevent a kid from using the movement that they have? You know what I mean? What if that, because it's the expectation is don't have the foot do this because the kid will never walk. But the probability of that kid walking was 0 to none. And then you're preparing that foot for standing up and preventing the use of the foot for the kinds of engagements that kid could have in these different ways with parents. And so, so that's the kind of thing that I feel that is really connected with emotion and your experience really of the world.
But it's also fascinating how it is about the expectations and how expectations shape
Yes.
our perceptions and hence also our actions, right? But this is all.
It's like the legalism, right? It's like the person can't walk. It's like you're less of a person. And, there are other ways of effectively locomoting, like wheelchairs and stuff. I think she had a question.
I was just gonna tack on to kind of the conversations about like the one ideal solution to a problem, or like seeing things from one scale, and how that is a limitation. I was listening to, which is kind of only tangentially related, this podcast earlier, and it was talking about how like the nuclear family is an example of one solution that everybody assumes is the only solution for how to raise a family, how to build an environment around a child or around like a unit. But it's not the only way cultures, or it's not the only way like different groups of people have done that thing. Like the way that we imagine building tall buildings is one way to do it, but it's not the only way. And I think the more we start to think about how we've kind of thought about things in a very specific way, because it's the way that keeps working, really limits our ability to see how easily it is for other people to look at the same thing and see all the ways it could be improved. And so I think that like that kind of ties in at every scale what y'all are talking about. It's like how we're limiting ourselves in even describing things. Maybe a limitation of language, it may be a limitation of like just literally not being able to think about a way that succinctly describes, like I know Tamara always talks about like how Germans have specific phrases that we don't even have to describe concepts in a very succinct way that we would have to take a sentence. So there's just so many ways to kind of reimagine like our relationships with space and spaces in ways that could really benefit us if we just dispel the idea that there's one thing that we should be looking for, and if we don't find it, then we failed. Maybe I'm just ranting about p-values. Anyway, but yes.
Which that gets at the very heart of the area of science that I study, is they, at the end of the day, they want to be able to find a particle that they can detect, and then they'll know that thing is actually there. Mm-hmm. And a big question in this area of astrophysical research is that a reasonable expectation? Mm-hmm. Or are we just expecting it to be the same as it's been throughout the history of physics? There's a sense in which like, yeah, but it's worked every other time. But maybe this is going to be the first time where that comes into play and it prohibits us from figuring that out for exactly that.
Rumsfeld, known unknowns.
We quote that more often.
It comes up a lot.
Hi, thanks. I wanted to triangulate a little bit here between Robert and Melissa, okay. So I teach at 11, so I was still getting dressed and doing things like that at 9. So I was managing to listen to the takeaway this morning. There was a physicist, a Black physicist from the University of New Hampshire, Chanda Prescott Weinstein, who's just publishing a book called The Disordered Cosmos, A Journey into Dark Matter, Space-Time, and Dreams Deferred. And I thought what was interesting about this, oh, you know about that?
Oh, I love that book.
Oh, you did, okay. Oh, great, okay. So, you were discussing, Robert, about the racialization of places and neighborhoods and the affect of that racialization. But Chanda is interested in the phrase dark matter and the term, discussing that it's actually transparency rather than dark matter, but there's this term, this binaristic, black, white, dark, light, and racially then also coded understanding of dark matter that has implications for who studies the cosmos and who is able to imagine outer space. And she was connecting the problem of living in, inhabiting this white supremacist world, living within it, and the problem of feeling safe in your own apartment when you can be surprised in bed and shot as a Black person in this country, and how then you don't have time to imagine the cosmos because of that spatial vulnerability, like what it means to inhabit your place as a person of color in this world. And I thought it was such an interesting sort of conjunction of these two concerns, and I wondered if you had anything to say about dark matter and that.
Yeah, I mean, in some ways, I mean, there's sort of the answer in terms of like, it's in some ways scientifically a really bad name for it as well, in terms of like just not being a good descriptor of what it might actually be. In fact, we just don't know, we basically don't know anything about it. And so when we don't see something, we just are used to it being these sort of like voids, these empty things, these dark spaces. But it does bring in some of those aspects to it. I mean, one of the things that I'm really interested in is ways to rethink how we even approach or even think about bringing people into astronomy for some of those perspectives. I mean, one of the things that I do a lot of is citizen science kind of astronomy. It's called citizen science astronomy, and it's trying to figure out like, how do you bring in people who don't bring the same like history, the same background, the same presuppositions into astronomy. And so I work with this online collaboration where basically it's called Galaxy Zoo. And so anybody can log in and help scientists classify astronomical objects. And as it so happens, I've found a collaborator through there who is just somebody enamored by space, no training whatsoever, and has found, I study in addition to dark matter, this really weird other kind of galactic shape called ring galaxies. And he has found by himself, in the middle of the pandemic, thousands of these galaxies for me that nobody else has ever found. Just because he wants to do astronomy. And he's not a member of that space. He's not a traditional member of that community for a whole host of reasons. And he's become just this integral part of my collaboration because of all these situational factors, but also because science started to figure out, like, how do we open up this space for other people to come in, to people to bring in wherever they are and make more space for them.
And it's also that space in the mind. You were talking about having a mental space, that sort of freedom to imagine the cosmos, to have room for the cosmos in your mind.
But it's also,
Yeah.
okay, no, go ahead. So I think it's really important what you bring up, right? Because I think what you're pointing to is that it really matters well, the words we choose, but also the forms that we choose in order to translate and in order to bring things into a register where they can be put up for larger discussion. And I think it was really interesting how you all introduced your concepts in the beginning, because one thing that really struck me was the primacy of vision and all of that, and how this seems to be still kind of the sense that is so ready at hand when we think about knowing. And now as the conversation has gone on, it's very clear that this is actually multisensory. It's about various forms of perception. And so it is about integrating the different senses, but then also finding, I guess, at least for the kind of conversation we have here, which is, driven by words, finding the appropriate terms and language and ways of making that translation again between these different sensoria, I guess, and then the concepts we use. And I think it's always so deceptive almost to appeal to the sense of vision, but I think it has become very clear that it's a very flawed and kind of misleading translation and metaphor for the phenomena that we're talking about. So.
I think that in general, a lot of the problem is that a lot of these things aren't really in our experience, and so we don't actually have any language to describe them. And so we sort of do some poor analogies, right, that we sort of grab onto to sort of describe a thing that really is fundamentally outside of our experience.
Yeah, but those analogies all tell stories, right? And
Yeah.
that way you're fascinating.
And you can
There's a
get-
wonderful example with the dark matter.
And you can get trapped in the analogy. I think that's sort of what the dark matter
Yes.
thing says, is that you make an analogy and it's not the thing. Right? The analogy isn't the thing. It's just because we don't have any way to talk about it. But if you do the analogy wrong, right, you can get trapped, your concepts can get trapped on the analogy rather than the actual thing you want
I
to
wouldn't
talk about.
necessarily say right or wrong, these are already concepts where we are stuck in discussions that are already unhealthy most of the times. But going back to the question of dark matter, and what you were saying, it's essentially if you're looking, and you can start very easily with Joseph Conrad's Heart of Darkness, right? And then you have all these metaphors behind it and all the history behind it, essentially history that is incredible argument. And this means if you're using concepts like this, and we don't have other ones, and we have to speak in languages, and we're using analogies, essentially in science we do all the time, right?
Mhm.
The question is how can we actually think mental space, health space, intellectual space as something that is being always present while we use concepts like this until we actually learn to speak in other ways. Because most of the language is gendered, is racial coded, is age coded. So if you talk about the categories, because it's a white, male, yada yada, university system, right? So the question is, what do we do? And this is not a question I do believe we can answer, but we need to consider a space where this is present. So to use another concept of a space that we share, that we create, that might be fluid, and that is not stable. Most of all, it cannot be stable because that is one of the very different, really dangerous things.
Etymologists to take up space right now.
I think that's one of the places where science can really look to other fields, like both of your fields, to see how things are conceptualized differently. How do you break those spaces up and start to think about them differently? How do you make it not that you're all trying to go towards a specific norm, but how is it that you start to create that like adaptability for not bringing those who have a disability into the normal space, but rather making that space more open and inclusive for everybody, and reinventing that space sort of from the ground up to get at some of that.
And in fact, there's the kind of theoretical approach I take. We try not to explain perception and explain action based on our human capabilities, but do it in a way that's continuous with other living systems, like plants move. You have these beams that I helped a philosopher in your department study, they actually find poles and we can circle around it, and plants actually, they're seeing these poles. And we actually measured the movements of the plant with a pole and without a pole. There is more determinism in the movement of the plant when there is a pole around versus when there isn't. Like how it's crazy. I mean, it's actually measurable, and how can we explain, what plants receive? And that's why I said to you, Tanya, that the idea of mentally constructing space is a very human thing. Plants are adaptive; they move very restrictively, but they do move adaptively. But then when you start continuing up the animal kingdom, you have other animals that, are simple animals that we like ants. They can't figure out their space. They can figure out the shortest way to a source of food. If you've had ants in your house, they can crunch up and they're like in the straight line there. And we don't give geometry to ants, right? We don't tell that there's like a guiding ant that somehow measures space and measures the multiple distances and say, hey guys, follow me here. But that's how we think about movement. We think the brain is computing all of these things, and we tell the muscles, hey, follow along, right? And when you think about how, then there are explanations actually from people that study ants that are very interesting. That's just based on how they structure their own environment with pheromone. As they move, they put pheromone in. And if they're finding the food and coming back, the path that's shortest will be more filled with pheromone. And because they structure the world with pheromone and they follow the gradient of pheromone, they end up in that shortest path without the leading ant. It's self-organizing. because of how they interact with the environment. They shape their environment in a way that allows them to directly control their action. And actually, in terms of vision for movement is not the primary sense, right? If you lose your vision, if you close your eyes, you can still move. You don't get completely, there are limitations, but you can use a cane, there are things you can do, you don't stop moving. The few cases of people that lost the sense of touch from the neck down, there are very few cases, and if you're interested, there's a book called The Pride and Daily Marathon of Ian Warman. One of the people that actually found a way to become functional after it, 18 years old, he lost the sense of touch from the neck down. And the experience, I mean, we have an idea if you close your eyes what it means to move around without seeing. If you put like headphones and stuff, noise canceling device, you know what it is not to hear. I'm not saying we know the full experience of a blind and a person that can't hear. I'm not saying this, but we have a sense. Touch, we have no idea. What happened to this person when he woke up, the description is it was like a disembodied experience. He couldn't even move. That's an 18-year-old person that moved fine. And the condition he got only affected the dorsal roots of the spine. And if you know a little bit of physiology, that's just the senses. All the motor roots were fine. But he could not even raise his little finger. He said, I'm seeing my body. He said the experience was, I'm out of my body. I can't even do this. And we assume that there's this holes in your brain, the programs that are automatically making you move. Without that sense, he couldn't even move. And the marathon is because the process of him recovering movement and using vision to guide movement, he never became effective. You're thinking you're sitting there, no effort. Do you know how he has to sit? Nowadays, he's still living at work, he might have died. He's very old, if he hasn't. He has to strike himself to a chair because he can't talk while maintaining his posture. Because he has to use vision to control movement, you have to be consciously aware of your space, of where you are. And even sitting, he drives, but he has to be striped because he learned that he has to look at his hand. When he wakes up in the morning, what he talks about, I wake up in the morning, he's covered up, right? So the light has to be on because if the light's off, he can't see, he can't move. So he starts moving like this, like randomly, so one hand appears. And then through vision, he starts, and then he says, I think, therefore I fall, because he can't think and move at the same time. And that, to use vision to control the movement is simply not effective. Basically, vision locks us up to the environment, but the control of the shapes of your body that actually compose, that's touch. That's dynamic touch. That's our sense. You have a clear awareness. If I ask you to pay attention of how your body is configured right now without looking, that sense is there all the time. We're not moving automatically. We're aware in a way that we can't describe with words about how we're relating to the world through this weird sense of touch, right? That we know so little about. If you look at books of perception, human perception, vision will have like 80% of the book, then touch will have like this tiny bit of the book. So we know very little about it, but it's a sense that without it, we can't even think, right? That's what he says. He said, if it's windy, I can't go out because I can't predict. It's very weird. I would never have thought that without touch, that's what happens to you. But that's what happens. Yeah.
So we're taking from this that without seeing, stays.
Yeah.
You just need to feel.
Primarily, feeling space is I would say for our skill, it's.
I think I'm not sure if I'm getting any more questions that were. Oh, sorry.
Well, kind of a quick comment. One thing I thought that was interesting with all of your fields and relating into space is that each one of your fields historically were at one time illegal or thought to be impossible or against the way that the world thought.
Yes.
Like in every society, ever since colonialism started, has used a form of what they call inegalitarianism. And we're all indoctrinated with that convert that each group is different, you can learn this. And it's interesting because a lot of the newer sciences that we observe in the world actually came from ancient cultures to have that perception that people understood and they saw things in the macro and micro. Maybe not to a fine detail, but just the fact that, seeing things that were invisible and
Yeah, that would have definitely got you hung at the stage. You know,
and there's something outside the solar system, people that you were saying were disabled, they were hidden. The fact that environments are controlled, redlining and blockbusting this. So it's kind of interesting how those were allowed. I don't know if they were perceived first by the masses, and then it was like, okay, now let's set this idea where did it start smaller, and then everybody else was able to catch on.
It's sort of interesting. It's like, I think that, people often hear the Galileo story, and I think sometimes people actually take the wrong message from what that is, right? So part of it is, he had his telescope, and he said, just look through it. You can look through it, and you can see that there's moons there, right? And like the cardinal or whatever wouldn't look into it, right? And I think the people who don't understand about that whole thing is that there was an intense distrust of senses at that time period. Right? There was an idea that even more than just the religious aspect, it was that pure thought is all you need, right? So like a mixture of both like philosophy and religion, that like you reason things through, and that is, if you have come to it through pure reason, it's good and fine, and whatever your senses are just corrupted, material bad things. So if they say something that disagrees with what you've reasoned, then like your reason was the right thing, and your senses are bad and wrong. and so like Galileo showed his telescope, they're like, well, I don't care what you say you see through this weird devil tube, right? It's not. This is not. Like this is not like this. We have this picture that we've applied through thought. And if you're saying that you look through this and it's wrong, then I'm saying your tube is wrong, right? Because like your senses are stupid, right? And that's sort of like, that was very much like the way of thinking that like you reason it out, and like whatever you reason is in fact true, regardless of what you see or perceive in any way.
And it just highlights what I think a lot of times when we think about science is forgotten, is that science is always socially situated. And it always takes place in a society within a context where there are these values present that are going to directly impact what is normal and not normal in that space.
Yeah, I think that related to that, I think that, I think just for the entire concept of science to sort of become sensible, it had to be something where people got used to the idea where you could basically interrogate your environment and then believe, right? The concept of like asking questions about your environment and testing it out and then saying, well, that must be what's true, just was not a thing that people understood except like the thing that we think of as the primary way of gaining knowledge was not considered to be a valid route of gaining knowledge until really recently, right? And so it's sort of a thing where like if you don't even have that way of, if you can't even conceive of that, then you can't even ask these questions like, at all. And this is actually something I would say that this is, I have to sort of, when I teach my students now, I sort of say that I think we still sort of do this to some degree when we talk about the narrative of science. Like we tell the story of these discoveries where some smart person came with this idea that was like really novel, and they worked it out. And we talk about this all the time with like Einstein, where Einstein had this famous like thought experiments where he's like, I'm going to think about this like simple clock, and then I'm going to work out the geometry of it, and therefore things that are moving fast, time appears to go slower for them. And people are like, look at this big victory of his thought experiments. But like science, like the real idea of science is that once you've done that, you've only done the very beginning of the work, then you have to find out if it's true. Right, like Einstein could have made this amazing theory, and then someone went and tried it, and it wasn't right, and it'd be like, you just throw it on the fire, right? So it doesn't matter how beautiful it was. Like that, like it sort of died with their head. It wouldn't matter.
Or that it was all Einstein. In fact, a lot of Einstein's big discoveries just happen to be the next thing you would conclude.
He pulled together a lot of stuff. There was a lot of stuff sort of in the air that he pulled together.
I have to say that I could go on forever. It's like, if you know me a little bit, I admire it. But for the sake of time, I have have to all ask you to keep exploring spaces with whatever senses you have at your disposal, all of them, if possible. And I thank you so much for being here. Keep talking because, I mean, I hope we have demonstrated that we can make connections between very, very strange fields of science.